entropy automorphisms of rational threefold.
Okay, yeah, thanks for coming and for the chance to tell you about this stuff. I guess what I want to do today is talk a little bit about another type of question you can ask about rational varieties, which is what can their automorphisms look like? And especially what can their sort of dynamically interesting automorphisms look like? So I want to sort of explain two things. First, I want to tell you a little bit about how you can use some kind of MMP-style birational geometry to prove some things about threefolds with these interesting automorphisms. And then I want to also show a little in the other direction, how you can take constructions coming out of this dynamical stuff and give a counterexample to a conjecture in the MMP. OK, but let me start off with the definition and a lot of examples of these things I'm going to be talking about. So say we have an automorphism of, let's just say, a smooth projective variety over C so I don't get myself in any trouble. We say that this automorphism has positive entropy if when you look at the pullback map on N1 or on H11 equivalently, it turns out, there's an eigenvalue that's bigger than 1. OK, so why is this called positive entropy? It turns out that this is actually equivalent to having positive entropy.
What's N1?
Just Divisor's mod numerical equivalence. I mean, you can also just think H11 the whole time if you want. It turns out the eigenvalues are the same here. OK, but there's a theorem of Gromov and Yomdin that says positive entropy in this sense, in the sense detected on cohomology, is actually equivalent to positive entropy in the dynamical sense, which I'm maybe not really going to define, but it has something to do with saying that the map phi really separates orbits of points when you keep applying phi again and again. It has sort of complicated dynamics. I'll give you a lot of examples, I promise. And maybe I should say, so I'm not going to talk about the dynamical interpretation, but if you look at Oguiso's notes from the ICM last year, he has kind of a nice introduction to this stuff from an algebraic geometry point of view. But basically, positive entropy is something about your map separating the orbits of nearby points when you apply it again and again. OK, so the basic situation is this. In dimension 2, when you look at projective surfaces, they're not by any means classified what these automorphisms are, but we have a pretty good handle on what they look like. And there's many, many examples known. And rational surfaces especially are a really good source of examples. There are many ways you can blow up P2 at 10 or more points and then construct a positive entropy automorphism on the blow up. I think the first examples of this are from Bedford and Kim and McMullen about 10 years ago, maybe. OK, so dimension 2, again, we have a pretty good grip. But dimension 3, it's very mysterious. So you can get some examples just by sort of taking two-dimensional examples and taking a product with a curve. But if you don't want examples that are just coming from surfaces, they're far fewer. In fact, the sort of first interesting example of a positive entropy automorphism of a rational threefold was just constructed a year or two ago by Oguiso and Triang. So it's not at all clear what the basic situation is, whether there are a lot of these examples and we just don't know where to look for them, or whether, in fact, there aren't very many at all. But we know there are some. So what I want to do today is prove some results about what these positive entropy automorphisms on threefolds have to look like. OK, I promised you examples, so here we go. So let me start with a two-dimensional example that shows this sort of blow-up thing you can do in P2. And I'm going to tell you a construction that's by Jeremy Blanc. So here's what we do. We fix a cubic in P3. Sorry, in P2. And we just fix some general point on the cubic. I'll call it P. Now we're going to define a rational map from P2 to P2 as follows. So here's what you do. If you draw any line through P, in general, it's going to meet the elliptic curve at two other points, right? So you get P1, and then you get sort of two extra points, x and y. Now, if you have P1 and you have 2 points, there's a unique involution that fixes the 2 points, right? If it's 0 and infinity, it's just z goes to minus z. So we're going to define our map so that on every single line through P, it acts by the unique involution that fixes the 2 points where it meets the curve. OK, now there's a little problem here, right, which is that this isn't defined everywhere. It's only a rational map. And where do you get in trouble? Well, if the line through P is tangent to the cubic, you get P1 with only 1 point. You don't get 2 points. And so our map from P2 to P2 is not defined on lines where this tangency occurs. And there are 4 such lines. So OK, but here's what happens now. You can try to resolve this rational map from P2 to P2. And it turns out that it's not that hard to do. So you need to blow up your point P along with the 4 other points, P1 through P4. And in fact, it lifts to an involution on the blow up. So I'll call this tau P twiddle. So what we get is an actual regular involution on P2 blown up at 5 points. And not only that, but because of the way we constructed it, it fixes the curve E pointwise. OK, so I mean, this is an involution. It doesn't have positive entropy. But we can do the same thing again. So now pick a different point Q on the curve and do the same thing. So you get an involution of P2 blown up at some other set of 5 points on the elliptic curve to some other set of 5 points on the elliptic curve. OK, now you can do the same thing one more time. So you pick a third point R, and you get a third involution on a 5-point blow-up of P2. OK, now each of these things fixes the elliptic curve pointwise. And each of them is constructed by blowing up points on the elliptic curve. So if you just blow up all 15 points together, all 3 of these involutions lift to automorphisms of the blow-up. Of course, they all lift to involutions. OK, so this is P2 blown up at 15 very special points where the points are somehow related in the group law in the curve. OK, they're all involutions, but it turns out when you compose the 3 together, it's not an involution anymore. And in fact, it has positive entropy.
The 2 of them?
Sorry?
If you compose on the 2 of them?
If you compose only 2 of them, I think what happens is it has infinite order, but the pullback matrix, it has, I think, a 3×3 Jordan block with eigenvalue 1. So you do get infinite order on the pullback on cohomology, but not actually positive entropy.
So you're using the same elliptic curve, different points?
The same elliptic curve for all the points. So you do the curve, and you pick 3 different points on it. OK, I mean, to check that this has positive entropy, this is some claim about some 16×16 matrix having an eigenvalue bigger than 1. I Blanc checked it. I take his word for it, I think. But
you also need to check that, in fact, they act on the same surface. I mean, it's not obvious when you do this.
yeah, that's right. I mean, you also need to show that just blowing up these points resolves it. Yeah, so there's things to check. And I think this is a fairly typical construction of what these look like on rational surfaces. You come up with some very tricky map from P2 to P2. Then you find if you blow up some very special configuration of points, you actually get an automorphism. So here I used 15 points, but in fact 10 is enough. And the original examples by Bedford and Kim and by McMullen are on 10-point blowups. OK, so here's another example. Let's do some threefold examples now. Maybe I should have started with this one because it's it's not as fun, I think. If you take an elliptic curve and you just look at the abelian threefold E times E times E, there's an action on this by SL3. If you act by an element of SL3 with an eigenvalue bigger than 1, then you get a positive entropy automorphism of this abelian threefold. OK. So another thing you could do is you could take a surface example and then sort of turn it into a threefold example. So let me call this thing S blanc. If you take the projectivization of the tangent bundle, for instance, right, our automorphism of S induces an automorphism of the tangent bundle. And so you get an automorphism of this P1 bundle over the surface. I don't know. This is a little more interesting than just taking a product, but only a little. Okay.
It could be a lot more rank 2 bundles.
That's right. Yeah, I mean, you could take the trivial bundle plus nkx for any n or something. Yeah, so there's many ways to get P1 bundles. All right, here's another boring one. If you already have a positive entropy automorphism of a threefold and it has a fixed point, you can just blow up the point, and the automorphism lifts to an automorphism of the blow up. I mean, this is not a very exciting example, obviously, but it's going to motivate a definition in a minute. OK, here's another much more interesting example. And this one is the example by Oguiso and Trung that I mentioned earlier. So we're going to take E to be an elliptic curve, but to be an elliptic curve with complex multiplication. So we'll take omega to be a cubert of unity, and then take the corresponding curve. Oops. OK, now this thing has a order 6 automorphism given by multiplication by minus omega. So we can look at, just like with this example 1 here, but now there's an order 6 automorphism of this threefold just by the diagonal action of multiplication by this 6th root of unity. I think actually the same example came up in McCree's talk yesterday, right? OK, now E times E has a lot of automorphisms coming from SL3. Those all commute with just the diagonal action of this multiplication, and so they descend to automorphisms of the quotient. All right, now this action has some singular points, so this quotient is, I mean, the quotient is not smooth, but if you blow up all the singularities, you get a smooth threefold. And again, you get an action of SL3 by automorphisms on this threefold. OK, so the construction of automorphisms on here is easy. The thing that's a bit of a surprise is that this x is actually rational when you take this quotient of a torus. And that's what Oguiso and Trung proved. OK, so I think these are the basic examples I want to keep in mind today, and especially this last one, example 4, where we have some rational torus quotient with a positive entropy automorphism. OK, now a couple of these examples were sort of built out of examples of automorphisms of simpler varieties. So let's sort of make a couple definitions to encapsulate that. So we're going to say phi from x to x is imprimitive if there's a smaller dimensional variety y and a map from x to y such that the automorphism descends to an automorphism of the base. So we want the dimension of y to be less than the dimension of x. We don't want y to be a point. Here, although x itself is an automorphism, I'm only going to insist that the other maps be rational maps. And in particular, this map down here is just a birational automorphism of y. But the idea here is if you're interested in maybe dynamical properties of this automorphism, like the number of fixed points, this is, when you're in this situation, it's really going to come down to properties of this automorphism of the lower dimensional thing. And so these are
Birational invariance, so can you just define it for an automorphism of a field of functions?
Yeah, I think I never remember what the things are here, but I think that's right. I mean, if your thing is not an automorphism, if it's only a birational map, you don't really have a good pullback on n1 of x.
Sure.
It's a pseudo-automorphism.
Okay.
But yeah, that's right. I mean,
In this definition, the two maps from x to y are supposed to be the same.
yeah, sorry. That's right. So these should be the same, and then this is some birational automorphism of y. OK, so what's an example of an imprimitive map? All these P1 bundles, I think I erased it. If you take a P1 bundle over a surface, the automorphism of the P1 bundle is imprimitive because you have the map down to the surface.
Triangle generic liberals.
I think you don't need that. So the other way you can build an automorphism out of an automorphism of something simpler is in something like example 3, where it's just a blow-up. So in this case, I want all my maps to be regular. I want f to actually be birational. And I need to say something about y. Let's say that y has terminal singularities. So even if x is smooth, I'm not going to insist that y be smooth. And again, we want the automorphism to descend to an honest automorphism downstairs rather than just a birational automorphism. So what are examples of of not dynamically minimal automorphisms? Well, this example 3 where we blow up a fixed point, of course, this never gives you a dynamically minimal thing. But actually, the way I've set things up, this example 4 of Oguiso and Triang is not dynamically minimal either. And the reason is that, remember, our x we got by resolving this quotient thing. And some of the singularities on here are terminal singularities. So this automorphism of x does descend to an automorphism of something smaller. It descends to an automorphism where you blow back down some of the things you blew up here. So this is a caveat throughout my talk, is when I say dynamically minimal, when x is smooth, y doesn't have to be smooth. And this gets us into a little trouble, but it also gives some kind of fun things later on. OK, is this OK, the setup here? I can tell you some results now. OK, so the motivation for what I was working on was a question by Bedford, which is I showed you this example by Blanc, where you take P2, you blow up 15 cleverly chosen points, and you get a positive entropy automorphism. The question is, can you do the same thing in P3? So can you start with P3, blow up a sequence of both points and smooth curves, and then somehow construct a positive entropy automorphism on the blow-up? What happens if you try to take the two-dimensional constructions and just repeat them in dimension 3? You end up getting a map that's not an automorphism. It's a pseudo-automorphism. So it ends up with indeterminacy in codimension 2. So it's easy to get blow-ups of P3 with pseudo-automorphisms. But if you want an honest automorphism, it's not clear at all. And sorry, I'm being a little sloppy here. When I say smooth blow-up, I don't just mean that x is smooth and you get it by blowing up some subscheme in P3. By smooth blow-up, I mean a sequence of blow-ups of either a point or a smooth curve.
What do you mean by a
So a pseudo-automorphism is a rational map from x to x that doesn't contract any divisors in either direction. So it's an isomorphism in codimension 1. So there could be some indeterminate curves here. Yeah, so these things are pretty easy to construct in all dimensions. But if you want an honest, biholomorphic map, it's much harder. OK, so here's the first result. It doesn't quite answer the question of Bedford, but it's a little close. So say you start with something with no positive entropy automorphisms, maybe P3. And you blow it up, so you construct some smooth blow up. Of M. The statement is, well, maybe X has positive entropy automorphisms, but you can only ever get imprimitive things by doing this. So again, I don't know if there's a blow-up of P3 with a imprimitive automorphism. But if M is something other than P3, you really can get imprimitive automorphisms when you blow up. So if you take M to be P2 times P1, this, of course, has no positive entropy automorphisms. You can blow this up and get to a rational surface times P1. You can get to S Blanc times P1 just by blowing up 15 curves. Now, this has many positive entropy automorphisms. You just take the one on the surface and then any automorphism of P1. But they're all imprimitive because they all just fiber over the P2.
Dimension 3?
Yeah, dimension 3. Sorry, yeah. Yeah, in higher dimensions, I have no idea. OK, now this is sort of fun. It tells you that these constructions that work so well in dimension 2 don't work in dimension 3. But on the other hand, this is only telling you about automorphisms of an extremely narrow class of varieties, right? I mean, every surface is a blow-up of a minimal surface, but in dimension 3, that's just completely false. So this tells us about automorphisms of blow-ups, but things that are blow-ups are pretty uncommon.
Is M smooth here or terminal?
Oh, yeah, M is smooth. Everything has to be smooth.
So with terminal, it's not true?
I don't know. OK, but it turns out that we have this weird condition that X be constructed as a blow-up. But if you're willing to instead just try to use a run of the MMP on X, you can get some weaker statements that hold on any threefold whatsoever without, well, any smooth threefold without this weird hypothesis that you constructed it by a blow-up. So it's more or less the same argument. You just replace the hypothesis that it's a smooth blow-up by doing a divisorial contraction instead. So there's 3 cases that we get in this. Sorry, and I need to add the caveat that you also need to be willing to replace phi by some finite iterate. But this is not such a big deal. I mean, it's an infinite order automorphism, and so you don't lose much. OK, the first possibility is that kx is numerically 0. So this covers the abelian threefold examples that we saw before. There are also Calabi-Yau examples. And I mean, this is a much harder problem, probably, to say anything in these cases. OK, so it could be that kx is 0. It could be that phi is imprimitive. Again, there are many examples of this type just by taking P1 bundles or products or things like this. And the fourth case is that phi is not dynamically minimal. Sorry, the third case. And again, remember this tricky example of Oguiso and Trong where you take a quotient. That one counts as not dynamically minimal. So this is sort of far away from being a real classification. It's just, I think really what this is saying is if you have an automorphism of a smooth threefold, well, then either it's abelian or Calabi-Yau, essentially, or it's imprimitive, or it's coming from an automorphism of a singular threefold. But once it's not dynamically minimal and you descend to the case where y is not smooth, then I can't say anything more. But I think it's also, I mean, it's not at all clear what you should hope for in this case. OK, here's another thing you get out of the same construction. Say you have a primitive positive entropy automorphism of a smooth threefold. Kx is not numerically 0. I mean, I think this is especially interesting in the rational case. So this much is automatic. Again, x is smooth. Then there exists an invariant divisor for this automorphism. Now, I'm not sure how surprising you'll find this if you haven't seen a lot of examples, but it turns out that this is false in dimension 2. So this is definitely not something that really comes for free. So I think people actually believed this was going to be true in dimension 2 for a while. There was a question or a conjecture of McMullen that said if you have a rational surface with a positive entropy automorphism, then there has to be an anti-canonical curve. Like in this Blanc example, the cubic is anti-canonical. And if there's an anti-canonical curve, well, in particular, there's an invariant divisor. But it turned out that this is wrong. So there are examples in dimension 2 with no invariant divisors whatsoever. But once you go to dimension 3, then actually this is true. I mean, I should say that the reason this is true is not because the analog of this McMullen question is true. It's not that there's always an effective anti-canonical on a smooth threefold with a positive entropy automorphism. What happens is you have a contractible thing that's periodic, like the exceptional divisors when you resolve this torus quotient. OK, so let me give you just a hint of how you prove all these things. And here's what the main lemma is going to be that they all follow from. Just say you have a threefold that's constructed by blowing up a smooth curve. And that the exceptional divisor of this thing, I'll call it E, is not periodic for your, So say you construct your X as a blow up, and that your X has a positive entropy automorphism. And not only that, but the exceptional divisor of the blow-up has infinite orbit under phi. Then it follows that phi is imprimitive. And proving this is really the hard work, but I'm afraid it's a lot of cases, so I probably won't say too much about how it goes. But the point is basically it's pretty hard to fit infinitely many smooth, geometrically ruled surfaces into a threefold unless the threefold is a product. Somehow, once you throw in the condition that your thing is that you have this automorphism sending these to each other, you find that in fact the only way that you can have a positive entropy automorphism in the presence of a P1 bundle over a curve with infinite orbit is if there's a map from X to a surface and that all of these E's, all of these P1 bundles over curves are just preimages in the threefold of a rational curve in the surface. So I'll say maybe a little bit about this at the end, but let me tell you at least how the other theorems follow from it. So let's start with this sort of Bedford question, where we're assuming our thing is constructed by a sequence of blow-ups. Now what we need to do is somehow produce a smooth ruled surface inside X with infinite orbit under an automorphism. So what are we going to try? Well, what's a candidate for this divisor E? We should say, well, we got our thing by a sequence of blow-ups, so let's just take the exceptional divisor of the final blow-up. So this is not necessarily a ruled surface, and it doesn't necessarily have infinite orbit. Maybe we blew up a point. So here's what you ask yourself. You say first, is the exceptional divisor periodic? And if it's periodic, we replace by an iterate. We might as well assume it's fixed. And now the idea is that our automorphism should just descend to an automorphism of y, and then we just go down to y and try again. So you need to be a little careful. If E is P1 times P1 and the automorphism switches the rulings, it's not going to descend to an automorphism here. But you can just replace phi by phi squared again. And so after replacing by an iterate, we can assume it's periodic. If it's periodic, we then descend to y, and we get an automorphism of y. And y is itself a blow-up of P3, so we just apply the same argument on y. Right, and P3 has no positive entropy automorphism, so if we keep doing this, eventually we better get to a model where this thing does have infinite orbit, because otherwise we would have had to stop. OK, so we can assume that E is not phi periodic now. The other issue is that, well, this was a blow-up of points and smooth curves. Maybe E we just got by blowing up a point instead of a curve, and the lemma doesn't tell us anything. But here's the issue in this case. I mean, we'd have infinitely many P2s sitting inside our threefold X. Now, suppose that all of them were disjoint from each other. Well, then you have a big problem, right? Because each of these P2s is negative on a line contained in it. If they're all disjoint, that would mean they're all linearly independent in n1 of x. But this is impossible. So if it's a P2, two of these have to intersect. But now we have another problem, right? If you have a P2 in a threefold, and you contract it to a point, well, you're also contracting every curve in this intersection. And if you think about what the blowdown does on this other P2, you see that you're contracting a curve in a P2 to a point when you blow down, and you can't do that. All right, so I mean, that can't happen. So our final blow-up must be the blow-up of a curve. And that means we've now reduced to the situation of the lemma. So we have a P1 bundle over a curve, and it has infinite orbit under our map. OK, now this strategy is the same to prove the other theorem. Remember, the other theorem was if x is any smooth threefold at all, not assumed to be a blow-up, then either kx is 0, the map is imprimitive, or the map is not minimal. But the idea is the same. We're going to try to produce somehow a smooth ruled surface, a P1 bundle over a curve on x, and do the same lemma. So the first thing we ask ourselves is, well, is kx nef? I mean, the idea is to run the MMP and get this E as the exceptional of a divisorial contraction. If kx is nef, we're not going to be able to run the MMP. But this case has been studied by Deqi Zhang, and there's no problems here. The reason is basically, on a threefold, if kx is nef, it's semi-ample, because we know threefold abundance. If the Kodaira dimension of x is either 1 or 2, then the automorphism descends to the canonical model, which is either a curve or a surface. And in this case, I mean, this shows the map is imprimitive, right? It shows our automorphism is coming from an automorphism of something smaller dimensional, namely the image of the canonical map. OK, so we might as well assume that kx is not nef. And that means we can run the MMP, and there actually is a contraction of the MMP. Now, what could happen? Well, it could be a Mori fiber space. Right? If you're thinking of this, something like this P1 bundle over a rational surface, this is exactly what has to happen. Your Mori fiber space is just the blowdown map of your P1 bundle. All right, but there's a lucky trick here, which is this. So on a given threefold, the number of different ways it can be a Mori fiber space is finite. Right? So P1 times P1 times P1 has 3 different structures as a P1 bundle, but there's always only finitely many. This is a lemma of Wisniewski. So there's only finitely many Mori fiber spaces. That means if you replace by an iterate, your map is actually going to commute with one of these Mori fiber space structures. And it'll descend to an automorphism of the target of the Mori fiber space by some kind of rigidity lemma thing. I mean, roughly in this case, we're saying if your x is a P1 bundle, then the automorphism descends to an automorphism of the base of the P1 bundle. OK, so a Mori fiber space, we're OK. The last case is if we have a divisorial contraction. Now, the good news, this is where the smoothness comes in. Divisorial contractions on smooth threefolds are classified by Mori. There's 5 kinds of divisorial contractions you can get. One of them is that you did the blow up of a smooth curve in a smooth threefold. The other 4 are all you contract a divisor to a point. So in the cases where you contract a divisor to a point, which is almost all the cases, you argue just exactly like this. If the exceptional divisor is periodic, it descends to the next thing down, which means it's not dynamically minimal. If the exceptional divisor has infinite orbit, you get a contradiction, just like if you blew up a point in P2. So just arguing as before, this must be blow up of a smooth curve. And we're done by the lemma. Maybe the last thing I should say is there is no 4 on this list, right? On a smooth threefold, you never have flips. So it has to be either a Mori fiber space or a divisorial contraction.
First case, you explained the situation when Kadeira dimension is 1 or 2. So what about Kadeira dimension 3?
Well, if it's general type, the birational automorphism group even is finite. So you can't have positive entropy. In case of Kodaira dimension 0, there's a little more you can say that Zhang says, but it's tricky. Yeah, good point, though. So general type never have these positive entropy automorphisms. OK, so I mean, that's the gist of the proof. But there's kind of a frustrating thing here, which is this problem that you might do a divisorial contraction and get to something with terminal singularities, and then you're stuck. I mean, you can't continue the argument. And you might hope, well, maybe there's some tricky way that you can keep going by doing an induction on the MMP. Let me tell you what happens when you really sit down with an example and try to make this go. OK, so what example should we try? Well, let's do this Oguiso-Triang example where we took a resolution of a torus quotient. So we're going to run the MMP on this quotient of a torus. But so we start with this smooth threefold. And the first thing that we do is, well, this torus quotient had some singularities that were terminal. And so there's some sort of obvious divisorial contractions on this thing. Namely, you should blow back down all the exceptional divisors over the terminal singularities. So I don't know, there's 20-some of these things, I think. So now you get down to this terminal threefold, which still has positive entropy automorphisms. But there's no more obvious divisorial contractions. OK, but you know you can keep running the MMP, right? This is rational, so we certainly aren't done. And what you find is that actually on this terminal variety, you can find a flipping curve. You can just explicitly write down what the flipping curve is. The bad news is that your flipping curve has infinite orbit under the automorphism. And so if you try to then just pass to the x plus that you get after performing a flip, you don't get an automorphism anymore. You only get a pseudo-automorphism. And then I mean, this is hopeless. I don't think there's much more you can say in this case. Yeah, so. But something interesting has happened here. Namely, we found a variety with one flipping curve, and the flipping curve has infinite orbit under the automorphism. So we actually have a threefold with infinitely many different flips on it. And it's not so easy to find such things, I think. So let me tell you sort of an aside of what you can get out of this example. I mean, I should say, we've totally hit a wall here. I don't think there's anything more you can do. But there's sort of a consolation prize in that you get a counterexample to an old MMP conjecture.
Curves are pairwise non-intersecting?
No, that's the problem, yeah. Well, so x is terminal, so it has isolated singularities. And a flipping curve on a terminal threefold must go through a singularity. So in fact, all of these flipping curves intersect each other at these singularities. So once you flip one of the curves, you can't flip the others anymore. When you flip one, it, in fact, gets rid of the singularity. So there's no problem here for termination of flips. I mean, this sounds a little worrying, but But it's OK. Once you flip some finite set of these curves, you can't flip the others anymore. And yeah, they all intersect at the singular points of X term. So let me just remind you of something about the cone theorem. If you have a terminal threefold X, well, then the cone theorem says that the cone of curves on X has this sort of decomposition as the curves where Kx is non-negative, and then plus some countable set of extremal arrays spanned by Kx negative curves. Right? There's this picture you can see in all the books about the MMP. Well, maybe only in Rob's book, but the thing to think of is the cone of curves looks something like this in cross-section. There's one half of the cone of curves you know nothing about. This is the Kx positive part. And on the Kx negative part, it's sort of generated by just rays of curves. And now all the books are sort of careful to point out, you really can have infinitely many Kx negative curves. And these infinitely many curves have to accumulate on the plane Kx perp. And in fact, there's a standard example that shows that this actually happens, that you can have infinitely many Kx negative rays. Right? You take P2 and you blow up 9 very general points, or 9 points that are the base locus of a pencil of cubics. Right, if you blow up 9 points in P2, there's infinitely many -1 curves. All the -1 curves are Kx negative curves. And so you get infinitely many Kx negative rays here. The funny thing is it's actually not so easy to come up with any examples with infinitely many Kx negative rays that aren't just P2 blown up at 9 points. So you could take P2 blown up at 9 points, and you could take a product with something. This gives you some examples. You could blow up some more points. And you could blow up some more points and then take a product with something, or the other way. But here's the question. If X has non-negative Kodaira dimension, so this is a question from Kawamata, Matsuda, Matsuki. If X has non-negative Kodaira dimension, it's not uniruled, probably. Is the number of Kx negative rays always finite? Right, so this condition that the Kodaira dimension is non-negative kind of rules out all the stupid variations on this where you take products and things like that. Right, and the answer is that it's not. And we can use this Oguiso-Trung MMP example to cook up a non-uniruled threefold with infinitely many Kx negative rays. I mean, maybe I should say, in some cases, this is actually true. So if X is a surface and Kx is effective, well, what are the possible Kx negative rays? It's the components of Kx, and that's it. So in dimension 2, the answer is yes. On a smooth threefold, the answer is also yes, because on a smooth threefold, there's no flips. And again, there's only finitely many possible divisorial contractions. Again, the components of Kx. But once you go beyond surfaces and smooth threefolds, this doesn't work anymore. OK, so I sort of fake explained how to get an example of a variety with infinitely many flips by running the MMP on a variety with a positive entropy automorphism. The problem is this variety is rational, so it doesn't give a counterexample to this. But it turns out you can just take some branched cover of this, and you do get a counterexample. So I'm not going to go through all the gory details, but let me draw a picture of what this variety looks like that has infinitely many Kx negative extremal arrays. How can you actually make this happen? So again, where this thing comes from is it's some kind of branched cover of this other example. So our variety is actually going to have a map down to a curve of genus 1 or more. The general fiber of this map is going to be an abelian surface. It's going to be E times E. Now we constructed our thing as some kind of quotient of product of curves. And so we're going to end up with some special fibers of this map that are quotients of E times E by some automorphism over a point in the base that's the image of a point that's fixed by our thing. We'll get a quotient of E times E. So the bad fiber is going to have a component that's E times E mod tau, which turns out to be a rational surface. This is a classical thing, I think. OK, now remember, our quotient wasn't smooth. So we had to do some blow-ups and resolve it to get a smooth threefold. So in fact, there were many bad singularities on this, this singular fiber we got when taking a quotient. Now, we want a terminal threefold, so we need to blow up some of those singularities. And in fact, one of these singularities is KLT, but not terminal. So we blow it up. Now we're going to have a variety where the component of the fiber over this point in the base has two components. One of the components is this E times E mod tau. It's a rational surface. It's a very complicated rational surface. I think its Picard rank of its minimal resolution is 13 or 14 or something. But it's going to have a second component. The second component is the exceptional divisor you get when you blow up one of the singular points to make your variety smooth. So let me call that one F. OK, so what's the canonical class of this thing look like? Well, I didn't tell you how to construct the thing, so I won't tell you how to find the canonical class either. But it's the pullback of some divisor on the base, just some kind of ramification. And then plus the exceptional divisors you got when you resolved the singularities of your threefold. Right? And remember, this exceptional divisor we created by blowing up a point that was KLT but not canonical. And so it's going to come in with a negative discrepancy. In fact, the discrepancy is -0.5. OK, so now I want to tell you how to find infinitely many kx negative curves on this threefold. Well, here's where they are. They're actually very easy to see. So we have this component that's a rational surface. And it meets this other component of the fiber. Now, if you have any curve in this component that meets this other component, this curve is going to be kx negative, right? It's contained in a fiber, so it's going to be 0 on the part that's pulled back from the base. And it's going to meet this exceptional divisor we got with the resolution, which has negative coefficient because it was a non-canonical singularity. So any curve in here that meets this other divisor is kx negative. It turns out you can actually find one flipping curve in this component that meets it. But what happens now is that this variety has an action of SL2 fiber-wise, right? The general fiber is E times E, but the SL2 action descends to an action of SL2 on this very singular rational surface in the bad fiber. And it's going to send this single flipping curve to other flipping curves that also meet the thing. I don't know. I mean, I think it's kind of a funny example. But this is the sort of example I think you can cook up by taking these constructions from the dynamics and then thinking about what happens when you look at them from a birational geometry point of view. I don't know. Is this OK?
Kind of iterate so that the thing you blow up stays because right? No, I mean because you just take this SL2 action on the fiber, it will also move the extra. But you take an iterate to make sure.
So remember, this thing was created when we blew up some singular point, and the singular points are fixed by the SL2 action.
Oh, they're actually fixed.
Yeah, they're actually fixed. And so when you blow it up, nothing really happens on this thing.
Okay.
But here you see a lot of wild things happening. And so you get these infinitely many flipping curves. And what happens if you try to keep running the MMP on this is you keep flipping curves from this component, and the flipped curve appears in this component. And eventually you track this.
Why the base of this vibration?
Yeah, so I didn't really tell you how to do this. If you take the E times E times E mod tau, this has a map to E mod tau, which is P1. So the way you construct this family is you just take some higher genus curve mapping to P1 and pull back the family. And there's still enough flipping curves in that thing to get infinitely many And that makes it non-uniruled, right? Because through a general point on this fiber, there's no rational curve, because there's no rational curve in the base, and there's no rational curve in the fiber.
You take C equal to E.
Sorry?
Can you take E as C?
I guess you probably can, yeah. I'm not sure. Yeah, there should be no problem. I mean, you just take your map to P1 to not ramify over the image of the singular points on the threefold. So I think you can use any curve you want. All right, I'm almost out of time, but let me just give you a very vague idea of how to prove the key lemma. Of how does the positive entropy condition actually go in to tell you something about the geometry. So let me just remind you what this lemma was. So the assumption was we started with something smooth. We blew up a curve. We, by miracle, found a positive entropy automorphism of the blow-up. And the final exceptional divisor is not periodic for the automorphism. And the conclusion is that phi has to be imprimitive, that it has to come from a map to a surface. So the challenge is, sort of given this geometric situation, we need to cook up a map from our x down to a surface. I mean, in very general terms, right, we're given the positive entropy condition. This is just some kind of numerical thing about how does the action on cohomology look. And we need to turn this numerical condition into some actual geometric information. Right? Yeah, sorry, this has just a lot of steps. But let me tell you what the key things you have to know are. So the first is, OK, you think about this pullback map on cohomology. And what would happen if you just started with your favorite ample divisor on x, and you kept pulling it back under this map again and again and again? Well, when you pull back an ample divisor under an automorphism, it stays ample. On the other hand, just by linear algebra, when you keep pulling back this thing under a map, eventually its iterates are going to converge to the eigenvector of the pullback map, up to rescaling. And so in fact, that means that the eigenvector associated to this top eigenvalue has to be a Neff divisor. Again, you start with an ample, you keep pulling it back, it stays ample, and these things are converging to something Neff. OK, so there exists a Neff divisor on x. This is not a big surprise. The interesting thing that happens is that the d squared is 0. And this is surprising, right? Usually when you have a Neff divisor on a threefold and you take its self-intersection, it's not going to be 0. I mean, right? This is saying the divisor has numerical dimension 1. The reason d squared is 0 is basically if d squared is not 0, well, then d squared is an eigenvector of the pullback on n2, on h22. And the eigenvector of that thing is lambda squared. Now, there's some result on, I guess they call it log concavity of dynamical degrees. There's some relation between the top eigenvectors of the pullbacks on the various HPP groups. And you just contradict one of these inequalities if d squared is non-zero. I mean, I should say, you might have to replace phi by the inverse to make this true. Either the eigenvector one way squares to 0, or the eigenvector the other way squares to 0. But this really just comes out of the linear algebra.
Surface, you still claim this?
Yeah.
I see.
Well, it's a little trickier than that, but essentially pulled back from the surface. Yeah, right. If your thing did have a map to a surface, you would get Neff divisors of square 0. You pull back something on the Neff boundary of the surface to the threefold. So the existence of this divisor sort of hints that this looks like a divisor that's pulled back from a surface. And in fact, that turns out to be more or less true. Right, how do you use this? I mean, where does this ruled surface come in? Well, if you restrict your divisor to this ruled surface, you get a divisor on a ruled surface that's Neff and squares to 0. So it's Neff but not big. And on a ruled surface, there are not very many divisors that are Neff but not big. Right? A ruled surface has Picard rank 2. So up to rescaling, in fact, there's only 3 different divisors that are Neff but not big. And we can do this not just on E, but on all the iterates of E under our automorphism. So this is sort of a huge amount of geometric information. Is that this eigenvector D has to restrict it in a very special way to infinitely many different ruled surfaces. And it turns out that that is somehow enough to construct a map down to a surface. Right, but there's a lot of stuff to do to actually construct it. So I think I'll stop there. Thanks.
Questions for John? I guess, so, you could guess that any, let's see, positive entropy, primitive automorphism of the threefold comes from the KLT Calabi-Yau. I mean, that's what happens in this Oviso example. So
yeah, that's right. Yeah, I'm not sure if anyone would conjecture that, but there is a certain tendency in this direction. So one thing that's known is if you have a threefold, I think terminal threefold of non-negative Kodaira dimension, and it has not just one positive entropy automorphism, but two commuting positive entropy automorphisms, then Zhang shows it has to be birational to a torus quotient in a very specific way. So here we lost the condition of non-uniruled, and we also are only assuming there's one automorphism, but certainly sort of it's possible that that's true, that torus quotients are everything. I don't know.
Any further questions?
Do these e to the n mod tau, do they ever stop being rational?
Yeah, I mean, so it's easy to just compute what the discrepancies are, because it's some quotient similarity. I think, well, it's rational for n equals 3. I think it's uniruled up to n equals 6 or 7. But I think
5.
It's 5? OK. Yeah, rationality is not known even for the past dimension 3, I think. I mean, it would be interesting to know.
Any more questions? Not, thank John again.